So we're talking about today standard temperature and pressure. Now we've dealt with standard pressure before. We've used standard pressure when we were comparing liquids in table H. Now standard pressure is the pressure of the atmospheric gases colliding with the container or a hands or a body at sea level. And these are equivalents. We have 101.3 kilopascals and 1 atmosphere. Now, I have taught you millimeters of mercury and or torr. Even we've used PSIs, 14.7 pounds per square inch. All of those are equivalents to standard pressure, and they can be used interchangeably. Now, the Regents uses these two exclusively, but all the other ones that I'm teaching you could be interchangeably used for standard pressure, depending on the problem. So if we go back to table H, we remember that we have to use standard pressure when we compare something called normal boiling points. Now what makes them normal is that if we have liquids, we know that liquids can boil at any temperature as long as the vapor pressure equals the atmospheric pressure. So because of that, we can't compare liquids in their boiling points until we say, hey, let's make the atmospheric pressure standard. Let's make it one that we can compare all liquids to, and we can see that the one that vaporizes faster gets there the quickest, and the one that resists evaporating has a higher normal boiling point. It needs a lot more energy to achieve a vapor pressure of 101.3. As I've said before, the one who gets to the 101.3 line faster is the one who boils the quickest. Now, of course, we don't have to use 101.3. We could use what? 1 atm as our unit, okay? Or what? We could use 760 torr or millimeters of mercury. They're interchangeable. So for liquids, keeping the pressure standardized at this 1 atmosphere gives us the ability to compare liquids' boiling points that otherwise could not be done. Now, when it comes to gases, gases, because they're a little different than liquids, they always fill their container. Their volumes are not definite like liquid volumes are. So control for volume, keep volume constant, we need to standardize the temperature. So if you think about this, keeping moles constant, okay, or at least keeping, I should say, in this case, keeping temperature constant and pressure a known value, we can start comparing the value of the volume and how many molecules they have. So if you remember Avogadro's law I taught you, that volume was proportionate to the number of moles. That's when pressure and temperature are constant. So if I double the number of molecules in a balloon, I'm going to double the volume. So when we compare gases, we love to keep these two variables at some constant to compare them. And we'll see much later on in mole concept why that is so. But for now, standard temperature is 0 degrees Celsius and 273 Kelvin. Or I should say, of course we use the Kelvin temperatures in gas law problems, whereas the 0 degrees Celsius, although we know it's an equivalent, we don't put that in a gas law problem because it would give us 0 pressure, and we know there's plenty of pressure at 0 degrees Celsius, things we've already discussed. So these are our values. So anytime you hear at STP conditions, they're talking about pressure at sea level, whatever unit you'd like to use that's an equivalent, or these units, and of course the temperature is the freezing point of water, or 273 Kelvin. And that's important to know. So let's go see some gas law problems where we put this to use. So we've got a gas law problem here, and it says 7.7 liters of a brown gas is under a pressure of 3.4 atmospheres at 45 degrees Celsius. What is the new volume of gas at STP? So let's start, as we always start, with our combined gas law formula. It's the only formula we have in this course. Okay, so we have the current condition, and now I'm writing the new condition. Normally I would cross out one of the variables, but notice I have volume, that's liters. I've got pressure and temperature, so all three variables are being used. Of course, we know that with the combined gas law, we're assuming the moles are constant, the number of particles. So let's just start plugging in. So I have 7.7 liters of a brown gas under a pressure of 3.4 atmospheres at 45 degrees Celsius. Now, of course, the 45 degrees Celsius has to be converted to Kelvin temperature. I need a temperature scale that tells me how many degrees away from zero motion and 45 doesn't do it. So I use Kelvin equals Celsius plus 273, and we put our 45, and we add 273 to that. And that's a 3 there, and we add that, we get 318 Kelvin. Okay, that's my current condition, and part of the problem is trying to make sure your variables go with the right set of conditions. That's the first condition. Now, what is the new volume, the future at STP? So we're solving for volume, and the question is, what numbers do I put in? Because a lot of people would say, Mr. Gronsky, you didn't give me enough information to solve for this. But yes, I did. By saying STP, I'm saying use standard pressure. Now, my friends in chemistry, because I'm starting you with atmospheres, why don't you use an equivalent to standard pressure in atmospheres, which you should all know is 1 atm. And you can go to your reference table if you have to. Now, if I was to put 760 torr or 101.3 kilopascals here, when you solve for V, they would not cancel. So you use the same unit as you start with. Of course, standard temperature, okay, is going to be 273 Kelvin. You have to be in kelvins here. So when you say STP, the pressure is one of those equivalents at sea level. The temperature is 273. Okay, that's important. So those words describe those set of conditions. Let's solve for V. Okay, algebraically, we're going to put the following gets rearranged, and we have 7.7 liters times 3.4 atm times 273, and how that happened is algebraically I'm timesing both sides by 273 over 1, or a quick algebraic shortcut. I know I shouldn't do that, but the bottom number under your unknown will go to the top always, and the top number would go to the bottom on the other side. So algebraically, you'd come up with this. We're just rearranging our equation to solve for our unknown. You really should do this and not just blindly come up with a number. Because when you do this, you can look at your units and see if they cancel out. Now, I'm going to ask my students to do one more step. I'm going to ask them to take the 7.7 liters. Notice there's no other liters. I'm going to times it by, in this case, 273 Kelvin over 318. Notice I'm taking whatever's on top is still on top. This guy's on the bottom. Then I'm going to do the like units over like units. In this case, I did Kelvin over Kelvin. Now I'm going to do 3.4 atm over 1 atm. And notice the kelvins will cancel, atmospheres cancel. I'm left with liters. What I just did was I just made a mathematically equivalent expression so that you can clearly see what's going on here. Kelvins cancel, atmospheres cancel. The only unit left standing is liters, so I know it, and you would have seen if you would have put like 101.3 here, this would not have canceled. So it's always good to use your units. It really saves you. So when I take 7.7 times 273, divide by 318, times 3.4, divide by 1, I get 22. At some point, I'll get 22.48 liters. That's my volume. Now, of course, rounding to 2 sig figs will do 23 liters. Now, you're not done. Does this make sense? Well, my friends in chemistry, my pressure, wow, did what? Looks like it went down more than a third. So my volume should go up more than 3 times. So it makes some sense here that our volume, okay, went to 23, so it kind of more than what? Tripled. So that's your answer. So in any case, these problems are all similar to what we've done already. It's just that now we have the word STP. Now some question could say just at standard temperature. You know that temperature. All right. And so all these problems are still the same, but just now that we're incorporating the word STP and its equivalent.